It's your friendly math tutor, Miss C here, and today we are talking about sine functions, specifically how the frequency impacts the wave and its period. So this is one of the more challenging topics in trig, so be ready to take some notes because this is going to impact how we solve every equation. Before we get started on solving equations, let's make sure we know what the frequency and period are and how we identify them. So the big idea here is that every transformation is compared to y equals the sine of x. You know this if you've watched my other videos. This is true for frequency as well, and the frequency of a sine wave, y equals sine of x, is 1. So what you're going to notice is that we don't write the 1 where the frequency is typically located, and that is the number that is being multiplied by the x within the parentheses. So this is similar to how we don't write the 1 for amplitude. It's just there because why, as math people, would we write extra letters if we don't need to? Okay, so the parent function, y equals sine of x, has a frequency of 1. And what that means is one wave is completed in the sine wave's period. In this case, it's 360 degrees. Now, the period, right, we just talked about is 360 degrees. And that basically tells us how many waves occur in 360 degrees. So these two are really tightly intertwined. And knowing the difference is really important. And here is why. Here's the subtle difference. So let's look at definitions. So frequency is the number of waves completed in 360 degrees. You cannot find the period unless you know the frequency. And then the period is the number of degrees it takes for a full wave to occur. And we find this value by saying 360 degrees divided by the frequency. All right, before we get started, solving equations with frequencies other than 1 and therefore different periods, let's make sure that we can identify both the frequency and period in some practice equations. First up, we have y equals sine of 2x. Our frequency is 2. And again, we find that because the 2 is being multiplied by the x within the parentheses. The period then is 180 degrees. As a reminder, we say 360, which is the period of our typical sine wave. Sometimes we call it the parent function sine wave. Y equals sine of x is always 360. So we divide that by our frequency, which is 2, to get our period. All right, what that means is our wave repeats every 180 degrees. And if we're thinking about it as frequency, we could say 2 full waves are completed in the typical period of a sine wave, which is 360 degrees. So you could think about the sine wave going double speed. All right. Our next equation, y equals sine of 1/4 x. The frequency is 1/4. Again, this is the frequency here. And the period, it's huge. It's 1,440 degrees. Remember, we find the period by dividing 360 degrees by the frequency. Be careful when you put this in your calculator that you're dividing by 1/4, not 4. Pretty different answers there. All right. And what this means is one wave repeats every 1,440 degrees. You could also think of this as within 360 degrees, only a quarter or 1/4 of the wave is shown. Okay. Next up, we have y equals sine of 6x. Our frequency is, did you say 6? If you did, you're correct. That means our period is 360 is 60 degrees, and we find that because 360 divided by 6 is 60. So we could think about this as a wave repeats every 60 degrees, and we are going to have 6 full waves within 360 degrees. So that's like 6 times what we would normally have. Let's solve an equation with a frequency other than 1. Before we do that, I want you to think of frequency as well as something that you've probably already seen in other functions you've studied, like quadratics, as the frequency could be considered a horizontal stretch or shrink. It either squishes the graph together or really stretches it out. Same idea in principle as with other functions. So let's get started solving this equation. And I always ask my students to identify the frequency in the period before we even get started, because it's going to impact our solving. So I'm noticing I have sine of 2 times theta equals 1/4. Our frequency is 2. So I'm going to go ahead and jot that down over here. And then I'm going to just find the period right away. 360 degrees divided by 2 is 180. That is our period, and we'll come back to why that matters in a second. You can also see that our domain is from 0 to 360 degrees, and I've color-coded every complete wave. So our first wave within this domain is color-coded yellow. Our second wave is color-coded green. So you can see the 2 waves that happen within the 360-degree period. As normal, I also put on the equation y equals 1/4, because we're looking at where y equals 2 theta intersects with y equals 1/4. That's what this equation means. So you're going to see we're going to have 1, 2, 3, 4 solutions. Because our frequency is 2, that means the wave doubles within 360 degrees. It also means the number of solutions we have also doubles. All right, so the good news is you know how to start solving these equations already if you've solved with me before or you've solved sine equations in the past. We start by taking the inverse sine of both sides, and I'm going to do it the long way on this first problem so you can see exactly what I'm doing if you haven't watched my other videos. All right, so I've set this up by taking the inverse sine of both sides. And when I do that on the left side, the inverse sine of 2 theta gets rid of the sine. So it gives us 2 theta. And that equals the inverse sine of 1/4, which is 14.48 degrees. So this is your reminder that if you got something else, make sure that your calculator's in degree mode, not radian mode. So always a good thing before you start solving these problems is to make sure that you are in the right measurement mode. Okay, at this point, we're going to do what we always do. We are going to write our second equation that says that we have 2 values within 180 degrees. So I'm going to say 2 theta equals 180 minus the value we just found, which was 14.48. Okay, I'm hopping back over to my equation here. I need to, my blue equation. So I'm going to get theta by itself, and we do this just using the order of operations. We perform the inverse operation of multiplication, which is division. And when we do that, we get 7.24 degrees. Okay, this is one of our solutions because it falls within our domain. It's this one to be exact. Okay, now here's where the change happens. Normally, to find my second value, right, within our domain, we would normally add 360 degrees because a sine wave repeats every 360 degrees. Since a sine wave now repeats every 180 degrees, because that's our period, I'm going to add 180 degrees to find the value that is in the same position in the second wave, so the one I just pointed to. When I do that, I get theta equals 187.24 degrees. Okay, so that's my other solution. So this is the big change. When you're solving equations, you have to know the new period. Otherwise, you're going to find a value that is incorrect. Okay, now we're going to work the pink equation, which is the second solution within the 180 degrees. Typically the 180 degrees, but because we have a doubled up sine wave, it's actually within 90 degrees. So still solve the same way. So 180 minus 14.48 is 165.52. And again, we're isolating theta. I'm doing that by dividing both sides by 2. And when I do that, I get 165.52. Not 165 because we just did that. Let's try that again. We get 82.76 degrees. That falls within our domain, and it's this value right here. Remember, just thinking logically, you can do this when you're solving problems. If normally I have two values in the positive realm every 180 degrees, when I squish this graph together so that I can fit 2 and 360 degrees, that means that I'm going to have 2 values in half that time. So I need to have 2 values within 90 degrees. I do here. So I always think it's good to be thinking about that kind of reasoning as we're solving because it helps us make sure that we're being accurate. Okay, I'm going to add 180 degrees here because that's my new period. And that will give me my next value within this domain, which is 262 degrees, or 262.76 degrees. My pen is really lagging. Okay, and that's this value right here. So the big difference here is you do all the steps the same, like you isolate what's in the parenthesis first, you apply your property to show there's two values within 180 degrees on a normal sine wave, and then you manipulate the equation. The difference is, instead of adding 360 degrees to represent the period, you're adding the 360 divided by the frequency. All right, let's do another one. Problem is sine of half x equals negative 3/4. So let's go ahead and start by finding our frequency, which I'm going to highlight in green. So our frequency is half. And then we'll calculate the period of our function here. So we do that by saying 360 divided by half. And that gives us a period of 720 degrees. That means it takes 720 degrees for a complete sine wave to occur. Or you could think of this as only half of a sine wave occurs within the typical period of y equals sine of x, which is 360 degrees. So I'm going to go ahead and highlight here. This is 0 to 360 degrees. That's part of our domain. That's this part. And then I'm going to highlight the other part of our domain, which goes from 360, our whole domain, to positive 360. What you can see is that it's two halves of a sine wave. So we've got the bottom half of one sine wave and we've got the upper half of the other. It just continues on. So like usual, I've went ahead and drawn the line of intersection that we're trying to find solutions against for y equals sine of half x. And we can see that we're going to have two solutions, one here and one here. So it's in a different location than we would normally expect. All right, so we're going to go ahead and start solving this by doing what we always do, which is we're going to take the arc sine or the inverse sine of both sides of our equation. When I do that, I get half x equals the arc sine of negative 3/4. Make sure you don't drop that negative sign. And when I do that, I get negative 48.59 degrees. Okay, make sure your calculator is in degree mode. If you got something else other than that, that could be y. And then I'm just going to do my other property here. Ooh, I noticed this should be x, not theta. I'm going to say 180 minus, be careful here not to drop your second negative, 48.59 degrees. All right, and now I do just what I normally do, which is I solve. And when I have a fraction multiplied by a variable, I always multiply by the reciprocal because I don't like dividing by fractions. Personal choice, you do you. If you want to divide by a fraction, go for it. Get the same answer if you do it right. So when I do that, I get negative 97.18 degrees. That would be this point in our solution right here. All right, so here's the thing. At this point, I should check and see if I have any other solutions within my new period, which is 720 degrees. So if I add 720 to this value or I subtract 720 from this value, I get a value far outside of our domain. So that is not going to work. Okay, so this is my only solution, which we knew because we see the graph. I'm going to do the same thing on the other side now. I have half x. I'm going to go ahead and simplify the right side, which gives me 228.59 degrees. Again, I need to get rid of this half, so I'm going to multiply both sides by 2. When I do that, I get x equals 457.18 degrees. While this is a solution, it's not in the domain. So that's a problem because this is not our second solution because we know our other solution is here and it's negative. So if I added 720 degrees, I know that I would be way out of domain because I'm already out of domain at 457 degrees. So I'm going to deduct 720 720 degrees from this. So, and I do mean I am deducting 457.18 minus 720 will give us our other value, which is negative 262.82 degrees. That is our second solution, and that happens right here. As always, please check your answers by popping these solutions into the x value and making sure that you get out approximately negative 3/4. Our third and final problem has a domain from 0 to 180 degrees. You can see that I've highlighted that domain with a vertical yellow line that's at 180 degrees. And we have sine of 3x equals 1/6. So what that means is our frequency is 3. That means we have 3 complete sine waves in 360 degrees. I know our domain is only 180 degrees, but I wanted you to see what this looks like. So our first sine wave is green, our second sine wave is purple, and our third sine wave is orange. We are only looking at all of the green sine wave and half of the purple sine wave. And what this means for us is when we find the period here, okay, we say 360 divided by 3. That means the period is 120 degrees. That means our sine wave repeats every 120 degrees. So you can see this point right here, that's where 120 degrees is. And then the next time it repeats is here. So we have exactly 1.5 waves within our domain. So per the usual, I've gone ahead and the graph represents sine of 3x. This blue line right here represents y equals 1/6, which is where we are finding the intersection between sine of 3x with. So we have one solution here, and we also have these two solutions. Okay, what you're going to notice is from this point to this point, it's exactly 120 degrees. And then from this point to this point is exactly 120 degrees. So that's what the meaning of the period is. So let's go ahead and solve this and find our solutions. So I'm going to do what I always do, which is take the inverse sine of both sides. When I do that, I get 3x equals the inverse sine of positive 1/6, and that gives me 9.59 degrees. If your teacher wants you to write all those steps out, go ahead and do that. I didn't want to, so I didn't. So I'm going to do my property that says in a normal sine wave, y equals sine of x, I have two values within 180 degrees. So I take what's in the parentheses, which is 3x, and then I say 180 degrees less the arc sine of 1/6, or inverse sine of 1/6, which I just found, which is 9.59 degrees. It is really important to note that this process never changes, even with a period change. Okay, I'm going to go back to the left equation, the blue one, and I'm just going to work it so that I get x by itself. So I'm dividing by 3 on both sides. When I do that, I get a value of 3.2 degrees, and that is a solution within our domain. That's this guy right here. Okay, our period is 120 degrees. So because I'm so close to the bottom of my domain, I'm going to add 120 to get my next solution, which is 123.2 degrees. And that's this guy that we talked about right here. So the distance between these 2 points is 120 degrees. Okay, great. So we've got 2 of our solutions done, this one and this one. And now we're going to work the right equation and find the other 2. So we have 3x equals 171.41 degrees. I can divide by 3 to get x by itself. When I do that, I get 56.8 degrees. And that solution is within our domain. And that's this value right here. All right, once again, I can add or subtract 120 degrees. If I subtract 120 degrees from 56.8, I'm outside of our domain. But if I add 120 degrees, I'm going to be just inside of our domain. So I'm going to end up with x equals 176.8 degrees. And that's this value right here. So once again, the distance between these 2 points is exactly 120 degrees, and that's what the period is telling us. These are our 4 solutions. So if you did not have the graph, and most of the time when you're solving these equations, you're not going to have a graph, make sure that you plug these answers in for x. And when you do that, you're going to get out approximately 1/6. And it's approximate because we've rounded these answers off. All right, thank you for joining me to talk about and solve equations with frequency and period changes. Make sure to subscribe for more videos. Till next time, remember, you've got this.